Good morning, participants. Then next session will be handled by Mr. Bhargav DS. He is currently working as a research scholar in IIIT Tiruchirappalli. He has 5+ years of teaching experience. Uh, Welcome, Bhargav sir.
Thank you, ma'am, for the introduction. Is my screen visible?
Yes.
Okay, thank you. So, good morning, participants. This session will be about cognitive radio and role of cognitive radio in Internet of Things. Before going to cognitive radio, whatever the research domain or work we take, we can broadly classify it into four different categories. We can put in four different categories. The first one, it is radio frequency front end and signal processing capability. Second one, it is system based system capabilities. Third, integration of hardware and software. And the fourth one, network ability. So if we take the first domain, for example, if we go for a radio frequency front end, we'll go for implementation using circuits. In terms of signal processing, we'll go for coding methods. So whereas in system, we go for algorithms and design of protocols, management of those protocol, whatever we require for communication. So when it comes to integration of hardware, nowadays machine learning is in trend. Artificial intelligence approaches, machine learning principles can be used. And the fourth one, network, where security is of a major concern. So whenever we go for a communication model design, security aspect needs to be addressed. So we'll start with cognitive radio networks. I'll start with the basic radio. Radio is for transmission and reception of electromagnetic waves. So it is a transceiver. Radio is invented by an Italian engineer, Marconi. So scientist has developed and demonstrated the first long distance wireless telegraph in earlier 1880s and 1890s. So in 1901, Marconi has broadcasted the first transatlantic radio signal. So here, if we go for a design of a radio, the basic requirement is modulation and demodulation concepts. So either it could be of amplitude modulation or angle modulation, that is phase and frequency. So the below diagram, which has been put in the slide, explains the basic radio. So this can be broadly categorized into three blocks. One is RF front-end section along with antenna. Second section is all about conversions. So converters we have. And the third section, it is processing. If you take the second section, we have analog to digital converter and digital to analog converter, ADC and DAC. Likewise, we have one more converter, DDC and DUC, digital down converter and digital up converter. So as I mentioned earlier, it is for a transmission and reception of EM waves. It is going to function like a transceiver. It will have a transmitting path as well as a receiving path. In the receiving path, we have antenna front end section where you will have a low noise amplifier. Followed by that, you will have mixer and local oscillator. So this signal output of RF front end will be fed to analog to digital converter. So till this point, it is analog signal. So herefore, we are going to convert it into digital. Analog signals, we are going to convert it into digital. So this is actually the receiving path where we have the digital down converter. If you take this path from the baseband processing, we have digital up converter and digital to analog converter. This is the transmitting path. So in a radio, in a generic traditional radios, almost all the three blocks, either could be RF front end or converter blocks or baseband processing, most of the functions are implemented using a dedicated hardware. So whenever we go for hardware, in case of any complexities, we have to replace the hardware. That is the major issue. Furthermore, we have many challenges. We'll discuss each and everything in detail. So the first section, it is antenna section. It is for receiving or transmitting information. Here the information is encoded in the form of radio waves. So followed by that, we have RF front-end section. It is responsible for transmitting or receiving radio frequency signals from the antenna, and we are going to convert that into intermediate frequency signals. So RF signals, we are going to convert it into IF signal. That IF signals only will be fed to the converter blocks. As I mentioned earlier, we are going to convert analog into digital and vice versa. So digital up conversion will have in the transmitting path, and digital down conversion block will have at the receiving path. So it is going to perform modulation and demodulation operations in both the ways, transmitting path as well as in the receiving path. The third block, it is baseband section. So few of the functions I have mentioned here. Baseband section performs few operations like establishing connections, connection setup, equalization of signals, noise cancellation, and frequency hopping, coding, decoding, correlating the signals, etc. So this is all about the basic radio. I mean the conventional traditional radio, where we will go for a complete hardware design implementation. So if we go for a DDC or DUC design, or performing some operations, that is baseband processing operations, we need a large computing power. Okay, there involves the computational complexity in terms of power. Why? Because we are using a dedicated hardware in the conventional radios. Whereas in programmable, the next evolution, programmable digital radios has been introduced. In short, we refer it as PDR systems. So in PDR systems, we go for implementing baseband operations and link layer protocols using software. Some of the functions, we have software modules incorporated, and we'll be using those software modules. And even application specific integrated circuits are available for DDC and DUC operations. So that is the difference with the conventional radios and PDR systems. In software, We use modules like FPGA, field programmable gate arrays, DSP, digital signal processors, and GPP, general purpose processors, or combination of all these three. So the exact definition, the formal definition of software-defined radio is a radio in which some or all of the physical layer functions are software-defined. So what we are meaning it as software-defined in the sense the baseband operations we are going to implement using software modules instead of dedicated hardware. We are moving towards the software module usage. Considering the computational complexity in terms of power, we are moving towards the software defined and software capable, software programmable radios. So the necessity behind moving to software defined radios, the first basic thing is flexibility. So the system is flexible. Whenever we go for a combination of hardware and software, the system has some flexibility. Here, the flexibility is in the terms of real-time adaptations to various air standards and waveforms. We can operate in different frequency bands. It may vary based on the application and different bandwidths and modes of operation. So that is the thing we are calling it as a flexible system. And the second necessity, it is multifunctional and programmable. We can easily upgrade the software modules, like we can add more features and capabilities. Thereby, we can reduce the capital investment, that is revenue towards the new system introduction can be reduced. Since we are using software modules, it is easy to upgrade and moreover low cost and power efficient solution. This is the major reason we have moved from hardware traditional system to the software defined radio. Instead of a dedicated hardware, we are moving towards the software defined and capable. The major reason is power efficient system is the need of the hour. So furthermore, we have few advantages. That advantages can be broadly put into three different aspects. One is in terms of radio equipment manufacturers and system integrated perspective. So what benefit manufacturers and integrators will have in the sense the cost reduction. Whenever we go for easy upgradation, since it is a common platform architecture, SDR is a common platform architecture. So using that common platform, we can design and we can evolve different systems. So thereby we can reduce the investment. So that is the major advantage in terms of manufacturers and system integrators. If we go for a service provider's point of view, new features and capabilities can be introduced. Like whatever we have the demand in the market, immediately we can introduce the features. Say for example, if we take some mobile applications, we have some updations. For each and every month, we can see some sort of basic updations in each and every application. So here service providers will have the benefit of easy upgradation. They can introduce new features in the evolving applications without spending much cost revenue. And in terms of end users, the benefit is anyone can communicate to anyone at any time. That is the end user benefit. So a basic system evolution I have mentioned here. So it started in earlier 1970s, and now presently we are in fifth generation systems. So here it started with ICNIA, which means Integrated Communication, Navigation, Identification Architecture. So in the earlier days, it was for a completely military sector. As the years evolved, the system has been moved to the commercial sector. So here in 1970s and 1980s, whatever the systems we have, whether it could be IC, or Speakeasy 1 and Speakeasy 2 modules, all this is for communicating between different zones in military. Whereas later on, we move to the commercial sector. So here MMITS is a modular multifunctional information transfer system, and DMR is a digital modular radio. These are all some of the examples of devices evolved from software defined to cognitive. So after this 2004, like 2010 and present systems, like we have different generations, 1G, 2G, 3G, 4G and 5G. It all started with a basic mobile phone system for communicating, voice calls. Then we have gone for a global system for mobile communication. We had a GSM, GPRS. Then in third generation, it is international mobile telecommunications model. And later on, it is advanced mobile telephones, televisions, and next generation systems. Okay, that is the present day situation. So now we move to cognitive radio. So the difference with software defined radio and cognitive radio is, in software defined radio, we use software modules for implementing the baseband operations. In cognitive also, we will be using software for implementing the baseband operation. The one simple difference it is, here we have some control as well as awareness technique. Will have some control over the system, and the system will have some self-awareness that we don't have in the software-defined radios and systems. So according to Joseph Mitola, actually he is the person who has made a great research in cognitive radio network. We can refer him as a father of CRN. CR technology, what he has defined as, it is intersection of personal wireless technology and computational intelligence. So cognitive radio technology, it is intersection of personal wireless technology and computational intelligence. If we take the cognitive radio alone, the major aspect here it is, it can be programmed dynamically. On the field we can program, and moreover the system will have a awareness technique. Three different awareness we can classify it as. Self-awareness, that is, system will have some realization about itself. And second awareness, it is radio frequency awareness, which means the system where it is operating, it should have awareness about that a particular environment. That is RF environment, or RF aware we call it as. And the third one, it is user awareness. So the co-users present in the particular RF front end, other users present in the radio frequency environment. So this particular awareness SDR does not have. This intelligence as only in the cognitive radio. So what we can do with this particular cognitive radios? Why this particular radios has been introduced? We'll see to that. So the reason behind introducing cognitive radios is optimizing the usage of scarce radio resources. So researchers in this particular field has anticipated the scarcity of spectrum. So they have gone for a solution and came up with this particular cognitive radios to optimize the usage of scarce radio resources such as frequency and power optimization. And moreover, we can reuse the spectrum wherever and whenever possible. This particular system, cognitive radio, has the ability, as I mentioned earlier, it has some intelligence technique. It can find the underutilized spectrum. Wherever the spectrum is found not used, it can find out that spectrum. Excuse me. Shall I continue? Okay, fine. So radio spectrum underutility can be found out using this particular cognitive radios. That is, ultimately, we are marching towards green communication. Also, we can reduce interference to the other systems. These are all the basic advantages of cognitive radio. So here I have listed a few of the challenges in terms of implementing cognitive radio network. So that can be listed as spectrum sensing or dynamic spectrum access algorithms, architecture design, protocols for architectures, and security. So these are all the four major areas we need to concentrate in terms of cognitive radio network design. Spectrum management has four basic functions. The first one, it is sensing, then allocation, sharing, and mobility. So we have to sense the available spectrum. As I mentioned earlier, we are going to find out the underutilized spectrum. We have to sense the spectrum availability. Then we have to make a fair allocation among the users present in the radio frequency environment. So fair allocation in the sense will go for sharing methods, and finally mobility. In case if the actual user, say for example, one particular frequency band has been given license to some party X or Y, in the absence of primary user, that is licensed user, we are going to find out the spectrum availability and we are going to allocate it for secondary applications. For emergency applications, we can use that particular spectrum. So in case if primary user again wants to use the spectrum or frequency band, this unlicensed user has to move towards some other vacant space. So mobility is also a major concern here. We should not create any disturbance to the primary user. So if you want to design a system which has a better sensing, accurate sensing and sharing and mobility concepts, it should have three awareness. It should be user aware, RF aware, and self-aware. So all this awareness concepts incorporated in the system only will provide a better system. So if we take the first part, spectrum sensing, it has some requirements. Fast computation, system should be very fast enough. The computational ability should be very high and it should be reliable and secure also. Accurate sensing should be done. So we'll be discussing all these concepts in the forthcoming slides. So here I mentioned a cycle which we call it as cognition cycles. It has been referred from articles from Joseph Mitola. So here we have the spectrum sensing as one major block. After finding out the spectrum availability, we are going to make analysis. Analysis in the sense, so the spectrum whole can be classified into three different spaces: gray space, black space, and white space. So we are concentrating on this particular white space. So if we take a TV band, we call it as a TV white spaces. This white spaces, we allocate it for secondary applications. Whenever primary user is not using the spectrum, we can allocate it for the secondary users. But if we take this black space, we cannot allocate this black space, which means it is completely filled up with the RF interference. White space is completely free of RF interference, whereas black space, it is completely filled up with RF interference. So that particular spectrum cannot be allocated or reused. Whereas this gray space, it falls in between black and white, where we'll have partial interference. Suppressing that interference, like a cancellation of all the noises, we can allocate it for the secondary application. So that analysis we have to make. Once after sensing, we have to make an analysis, whether it is gray, black, or white space. Then we go for estimating of a channel capacity based on the application. Then finally we make a decision and we communicate back to the RF environment. So this is one cycle. The second cycle, we have phases of cognition: observe phase, orientation, plan, decide, act. So and the new phase, it is learning phase. So for this particular spectrum sensing only, here I've mentioned this particular diagram. So first we are observing the spectrum availability, then we are inferring some context from that spectrum availability. Like we are classifying it as gray, black, and white spaces. And priority, say for example, if three secondary users are there for using the spectrum, so we have to prioritize whom to allocate. That is the orientation phase. So establishing priority, and we have to consider whether it is immediate operation or urgent or normal operation also. If it is immediate operation, directly we go for a action phase and we communicate back to RF environment. If it is urgent, we go for a decision phase, allocate all the resources. As mentioned, we use FPGA, DSP, and GPP resources. If it is normal, we'll go as per the plan. We'll go for planning phase, we'll generate all the pros and cons, we'll evaluate all the alternatives, and then we go for fair allocation of resources and action phase, and we communicate to the RF environment. So this is a basic cognition cycle. So with this cognition cycle only, we are going to sense the spectrum. So sensing is the first part in the CRL, first design challenge. So here I have mentioned few classifications of spectrum sensing. So in classification 1, we can put in three different aspects. One is non-cooperative system, which we even call it as a transmitter detection. Second one, it is cooperative system. It comes under receiver based detection. Third one, it is interference based. So in transmitter based detection, we have different types like energy detection, matched filter, cyclostationary. All these three comes under narrow band sensing. So here in energy detection, the spectrum sensing completely depends on the signal energy. Whereas in matched filter, we should have some prior knowledge about the users in the environment, primary users and secondary users available in the radio frequency environment. That information we should have, prior information we should have for sensing. The third one, it is feature-based detection method. Apart from these three, we have waveform-based, wavelength-based, and multiple antenna-based spectrum detection. All this comes under a transmitter-based system. Whereas in the second category, received-based system, we have centralized and decentralized system. If you go for a combination of centralized and decentralized system, it comes as a hybrid cooperative method. So why we are moving from a transmitter system to receiver system in the sense the transmitter alone cannot communicate to the other users. We'll have problems like shadowing effects, receiver uncertainty, all those. In order to avoid and address all those problems, we are going for a receiver-based detection also, which means both the users are going to sense and communicate. There will be a mutual communication between the transmitter and receiver. Third one, it is interference based. So we cannot limit the system design with transmitter and receiver alone. We have to consider the noise cancellation and interference cancellation also. Say for example, if we set a threshold, we'll have a threshold example as 0.5. Whichever value lies above 0.5, if I take it as signal, and the value which lies below 0.5, we take it as noise. So here, the value which lies between 0.5, we have to suppress that particular signals. Why? Because we have considered it as noise and we have to suppress that signals. Noise cancellation has to be done. Then we have to make a fair allocation to the secondary user. So for this, interference based systems is required actually. Second classification, it is narrow band and wide band sensing. So few of the types I have mentioned here, narrow band and wide band sensing. So here we discuss all the sensing methods. As I mentioned earlier, these are all the blocks representing the users present. This particular space is left unused. So in this entire band, we have three blocks, which means three users are present. We'll consider it as, for example, three users present, and we find spectrum availability here and here as well. So here we classify it as a gray, white, and black space, and we go for allocating it to the secondary user. So primary user comes under licensed category, secondary user comes under unlicensed category. Whenever primary user want to use that particular band, secondary user has to migrate to the some other spectrum availability, which means the system should continuously sense without any break or gap. The system should have the capability of sensing the information continuously. Not only sensing, the sharing operation has to be done, mobility operation has to be done, and all this information has to be communicated back to RF environment. So that is the thing I have mentioned as awareness technique: user awareness, RF awareness, and self-awareness. So this process, the system should have self-awareness and it should communicate to the other users and it should communicate to the environment, RF environment. So if we find some vacant space and if we made allocation for one spectrum, one secondary user, we have to communicate to the other secondary users. Why? Because there should not be any disturbance between secondary users. So for analyzing and making allocation, we have an hypothesis. We call that hypothesis as a binary hypothesis. So which I have taken it as H0 and H1. Say for example, H0, I have found this particular spectrum hole. Okay, it is a true detection. We take it as for example. H1, signal not detected. Information, we don't have any information about the spectrum availability. So if we take analytical expression, we can relate H0 equal to some signal, some X of t or Y of t, user signal. So H1, it is noise actually, completely noise, where we cannot place the secondary user. So this true detection and not detected H0 and H1, how we are classifying in the sense, earlier I have mentioned as some threshold value. Whichever the signal value is lying above 0.5, say for example, I am taking it as signal, primary user signal. If it is less than 0.5, I am taking it as noise. So I am going to suppress that noise and I am going to place the secondary user. But here lies the challenge. Sometimes noise may dominate, which may be above 0.5. In that case, we'll have a consumption that primary user is present. Actually, beyond the threshold level, we are having the noise signal. So in such cases, what happens is it may lead to missed detection. Actually, we think it as a signal, but beyond the threshold level, we are having the noise. So that leads to missed detection, missed spectrum opportunity detection. One more case also we have here. The signal, whatever is lesser than 0.5, we are taking it as noise normally. Signal also will have lesser strength. Okay, signal strength, if it is very weak, it may lie below 0.5. In such case, what we think is it is actually noise. That is the thought we will get, but actually primary user is present. If we try to suppress that particular signal, it may lead to disturbance for a primary user. It creates unwanted disturbance to primary user. That comes under false alarming. That is false alarming. Actually, these two, it is hypothesis for classification of primary user present and absence. And the bottom two, misdetection and false alarming, is actually a region of confusion. We have to classify whether it is signal or noise. Sometimes beyond the signal level, noise also may dominate. Sometimes the signal may have lesser strength. In such cases, we may miss the spectrum whole in detection perspective, or we may give a false alarm to the secondary user. So this has to be avoided. For this sake only, we are going for interference based system design. So beyond the threshold level, we have to set basic noise floor level. Then beyond that noise floor level only, we have to set the threshold level. Thereby we can accurately classify the signal and noise. So these are all the design constraints involved in spectrum sensing. The next it is protocol architecture and network security requirements. So whatever the communication we take, it can be related with, it has reference with the OSI model, Open System Interconnection Model. So in each and every layer, we'll have some protocols. So design of adaptive protocol for all these layers is a great challenge. And design of cognitive engine is another important aspect which needs to be concentrated on. If we take this particular data link layer or network layer, we'll have some security issues also. We'll have layer attacks, routing attacks, and traditional CRM specific attacks. Okay. In each and every layer, we have some security issues. So design of adaptive protocol which supports better communication as well as which deals with all the security aspects is the need of the hour. And even we can go for a cross layer design and addressing upper layer challenges also. In the forthcoming slide, we'll discuss cross layer issues and upper layer issues. So in the previous slide, I mentioned about cognitive engine. Actually, cognitive engine is the intelligent core of cognitive radio architecture. So if we take CRN, cognitive radio network architecture, the intelligent core is the cognitive engine. So where we'll have all the system learning and adaptation algorithms. So software system needs some learning and adaptation algorithms. The system needs to be trained here for finding out the spectrum. So basic operations performed by cognitive engine, here it is modeling, learning and optimization process. So again, optimization is a thing need to be addressed for designing a reconfigurable communication system. If we analyze in detail this cognitive radio engine, we'll have three domains: user domain, radio domain, and policy domain. So user domain is going to pass all the necessary information to the application, user application, which are all required for, it helps in directing the cognitive engine's optimization. Whereas if we take the second domain, radio domain, it consists of all the RF and environmental data. So this environmental data we need to be analyzed. Say for example, if we are having any propagation issues or fading effects or interference effect, that need to be addressed here. So this leads to this propagation effects and the interference sources leads to degradation in system performance. So this has to be avoided. So all that information this radio domain is going to provide us. User domain is going to have the necessary information for optimization. Radio domain will have environmental related data, whichever is going to affect the system performance that needs to be addressed. And the third domain, it is policy domain. Policy domain is for making fair allocation between primary and secondary users. This has been formulated by regulatory bodies. Okay. That information will have in the policy domain. So the major objective here is we are going to observe the spectrum and we are going to learn the environment and we are going to learn about the users in that particular environment. That is what we are calling it as awareness and learning capabilities. So if we take the optimization, machine learning has made a huge breakthrough in the fields of AI, artificial intelligence applications. Like if we use hardware like graphics processing unit and field programmable gate arrays, FPGAs in AI applications, GPU has better compatibility with ML algorithms and provides high computational speed. Why? Because instantly we have to sense the spectrum whole and we have to communicate to the secondary user. Secondary user has to use that spectrum. In case if primary user again comes into picture, we have to move towards the some other vacant space. So here speed is also an issue which needs to be concentrated. So here compatibility and speed we can achieve using a graphics processing unit and optimization wise, if we go for usage of support vector missions, Sequential minimal optimization SMO is the conventional training algorithm for a support vector mission. But here we have a shortcome. It does not scale well with the data size. Here, data processing is also an important issue. So we have to scale along with the data size. We are not going to deal with the small data here. So we need a system with better scalability. We can go for stochastic and gradient descent algorithms. We have different classifications in SGD, stochastic gradient descent. We have a different classification like ADA-grad, ADA-delta, RMS prop, and ADAM. These are all the popular training algorithms for achieving high speed, scalability, and like we can go for parallel processing. So that is possible here. So objective is to optimize the system design. So this is what the concepts I was explaining so far. I'll have a licensed as well as unlicensed band. Likewise, licensed user is primary user, unlicensed user it is a secondary user, which we call it as XG. So here in licensed category, primary user makes communication with the primary base station. In case if primary user is not utilizing the spectrum broker will communicate to the XG base station, secondary base station, and secondary base station is going to make allocation with the users here. So here comes the cooperative mechanism, non-cooperative mechanism. While allocating the spectrum, it comes under a centralized allocation, distributed allocation, all those. So while discussing the protocol architecture, I mentioned about a cross-layer design and upper layer issues. So this has been correlated with mapped with OSI model here. So if we take the sensing part, major sensing functions happen in the physical layer. So that is what the definition says. Some or all of the physical layer functions are software defined. So the major spectrum sensing happens in the physical layer. Some portion it lies in the link layer also, data link layer also. Whereas if we take the sharing part, spectrum sharing, we have the major spectrum sharing function in the link layer. Link layer is responsible for spectrum sharing. Few of the operations happens even in the physical layer also, which means both the functions are happening in both the layers. So here XG network functionalities require a cross-layer design approach, like an adaptive system. So spectrum sensing and spectrum sharing, if both are cooperating with each other, it leads to spectrum efficiency. So efficiently we can allocate it for secondary applications without any disturbance to the primary user. So apart from that, we have a mobility and management functions also. Whenever primary user want to use the spectrum, we have to move to the some other vacant space. So here, the major research is on spectrum sensing and spectrum sharing, like designing a system with a cross-layer approach, an adaptive system. So again, all the protocols also comes into picture here. Physical layer, this second, third, and fourth layer protocols design and addressing all the security issues has to be done for a better system design. So I have classified into two: physical layer, RF functions, and baseband processing. MAC layer as a wireless sensor network, where link traffic has to be controlled, avoiding collision, optimizing data throughput, reducing latency, all those need to be addressed. These are all the two major layers where research is going on in CRN. One example I mentioned here, if you go for underwater communication, like design of acoustic and remote sensing technique. So under the water, we have to measure some parameters like temperature or humidity. Like over the water also will have to sense some of the parameters, even salinity and like oil spillage. So for these monitoring applications, we can design and deploy a system like a design of a radar. We can deploy a sensor node. Okay, cognitive radio also can be deployed as a sensor node for sensing all this. So coming to the fourth category, spectrum sharing. Here we have different models like dynamic exclusive usage model, open share model, and hierarchical access model. So actually this classification we can put into three: level 1, level 2, and level 3. So this level 1 is authorized models for spectrum usage. Regulatory bodies will have some legally framed rules and regulations for spectrum usage. That is the level 1. Level 2 deals with spectrum access approaches, how we are going to access the spectrum frequency bands. And level 3, how we are going to share among the users. So here is the major issue: spectrum sharing, whether we are going for centralized sharing or decentralized one, whether any central entity like a hub or a spectrum broker is going to allocate it for secondary users, or a decentralized usage will be done. If we go for a decentralized one, a collision may occur among users. Whereas if we go for a centralized one, a fair allocation can be done. But in both the methods, we have a pros and cons. So here, role of cognitive radio in IoT. If we go for incorporating CR, cognitive radio with IoT technology, a more intelligent system can be designed. A more intelligent system which has high accuracy in spectrum sensing, spectrum mobility management, and sharing aspects, that can be done with high speed. Moreover, it should be scalable. Parallel processing operation needs to be done, and it should be reliable and secure as well. So if we incorporate CR with IoT technology, all this design issues can be addressed. A more intelligent and high-speed network system can be designed through wired as well as wireless communication technology. So cognitive IoT is the use of all available computing technologies along with the data generated by the connected devices. Whenever we talk about Internet of Things IoT, we'll have number of devices connected. Each and every person nowadays we are having 2 to 3 devices, for example, maybe even more than that. So computational complexity is getting increased here. So cognitive IoT helps in computing with the data generated with all the connected devices and actions performed by all those connected devices. So if we incorporate both CR with IoT, a better system can be designed. Thank you.
Thank you for the wonderful session. The session was very informative and very well explained. Thank you so